Hello everyone, I'm Joe. Today, let's continue to talk about modular combinational circuit. And today's topic is decoder. Before we move into decoder, let's clarify some of the confusive concept. So, in many cases, when we're looking at the logic diagram, we are seeing kind of bubbles, like little circle. Sometimes we see these bubbles at the input or output of a logic gate. For example, sometimes we see things like this, right? So what does that mean? So if we see a bubble at the input or output of a logic gate, it means the input or output should go through a lot function, go through a lot, like going through a lot gate, take the lot function. But if we see a bubble at the input or output of a modular circuit, like a decoder, encoder, or anything we're going to talk about in the following few topics, okay, this bubble means the active levels. So they don't necessarily mean there's a lot gate as the input and output. There might be, but that's not what we care about. We care about here is that the bubble tells us which logic level to activate this device or this chip. Okay, if you see the bubble, means that the input or output is active no, which means 0 will activate that line. Okay, if you don't see a bubble, which usually means logic 1 will activate that input or output. By definition, a decoder is a digital circuit to activate one or more circuit outputs upon detection of a particular digital state. So decoder, in other words, you can think decoder like we input a code or password, and the chip or the circuit based on the password, the circuit can activate one of its output to give out an active signal to control other things. Okay, and to name the decoder, we use the input and output number. So for any input decoder, we can have maximum 2 to the power of n outputs. So we can read it as n to 2 to the power of n decoder or 1 of 2 to the power of n decoder. Then y is n and 2 to the power of n. Basically, from what we learned from binary number, for n input variables, we have 2 to the power of n's possible combinations. Okay. For example, for a 2 to 4 decoder with active high input and active high output, we have the symbol look like this. You can put a decoder or just deck, and we have 2 input. You call them A1 or A0, which means the input. Sometimes you can also use D, letter D, doesn't matter. The output, most time we just use Y, and so by using these 2 inputs, we can control maximum 4 output here. We call them Y3, Y2, Y1, and Y0. So what will happen is that based on the values for A1 and A0, one of the output will be put to the active level. Here, you see no bubbles in this, right? Which means both inputs and outputs are active high. So let's see, 0, 0. For 0, 0, the corresponding decimal value, the output with decimal value 0 will be activated, which means it will be set to 1 if the input is 0, 0. And the other output will be 0 if the input is 0, 1. So also here we just by default we assume that A1 is the MSB and A0 is LSB. Okay, so 0, 1 corresponding to decimal 1. So the corresponding output line will be set to 0, or set to 1, which is active level, and other will be set to 0. 1, 0, which is decimal 2, so Y2 this time will be activated. Y3, Y1, Y0 is not activated. Finally, 1, 1. This is decimal 3, so Y3 will be activated. Okay, so that's the truth table for the 224 decoder. We will talk about the detailed logic circuit inside the decoder later on, but right now we just talk about this circuit as a module. Okay. Then how about the 224 decoder with active high input and active low output? Since the input is active high, so basically it's the same. We got A1, A0. But the output is active low. To represent active low, we need to put a bubble. One more time from previous slide. The bubble doesn't mean they are taking a lot. It simply means they are active low. So when they are activated, they should output as 0, not 1. But also to reflect this, we also make change to their names. So instead of Y3, we call it Y3 bar, or Y2 bar, Y1 bar, Y0 bar. Okay, so the truth table for this decoder look like that. Okay, 0, 0. Now still the Y0 bar will be activated, but now the active level is 0. So you need to put 0. The other is not activated, so you put a 1. 0, 1. So Y1 will be activated. 1, 0. Y2 will be activated. 1, 1. Y3 is active. So that's the truth table for the active low output decoder. Okay, so for the example I gave you before, we can see that at any time, at least one of the output will be active, right? Because there's no switch to shut the device down. So like there are always some logic levels at A1 and A0. So the corresponding output will be active. But what if we want the device to be idle, or okay, the stop it from output any active output? What we can do is to add an enable input. So just add another input here called enable. Right now, for this example, we want an active no enable. So we should put a bubble here, and you'd better put a bar over this name here, so it tells people this is the active no input just by looking at that name. Okay. Then the truth table of this new decoder should look like. So we need to add this enable input here. A0, Y3, Y2, Y1, Y0. So if enable is not active, because it's active no, so not active means it's equal to 1. If it's equal to 1, then it doesn't matter what value you have in A1 and A0, the output always deactivated, which means they are all 0 in this case, because they are all active high. So this decoder only works when the enable input receives 0. Then it has same truth table as before. So it should look like this. Okay. So basically you can think the enable input as a switch. If it's in active level, the decoder works properly. If it's not in active level, the decoder doesn't work or output is not activated. Okay, let's look at another example. This is a 328 decoder, and there are some commercialized product here. So it looks like this. Actually, it has 3 inputs. So C is the MSB, A is the LSB, and then it has 8 outputs, and all outputs are active low. You can see the bubble here. Okay, and for this one, it has 3 enable inputs. Both the 3 of these are enabled, and they must be active at the same time, so that this decoder will work. And we can tell the label is not showing that, but the diagram shows that we have 2 bubbles here. So these 2 inputs are active low. This input is active high. So basically, if you want this decoder to work, you need to set G2A and G2B to 0 and G1 to 1. Okay. So now let's look at what's the truth table look like. So if G2A equal to 1, which means it's not active. So I told you that all these 3 enable input must be active at the same time. Since G2A is not active, then no output will be activated. So everything equal to 1. Why it's 1? Because the output is active no. Okay, not active means 1. Then if G2B is 1, so G2B is not active still, the decoder won't work normally. And if G1 equal to 0, also it won't work normally. Now, if these 3 enable inputs are active at the same time, then the decoder work properly. And so 0, 0 corresponding to Y0, and then it should be activated, which means the output 0, and other output are not activated. 0, 0, 1. So Y1 will be active, others will not be active. 2. Basically, you probably can tell the truth table would look like this, and all the others blanks are 1. So at any moment, only one output is active. Okay, so that's a truth table. So now you know, once you have the data sheet of a given decoder, actually not that's the full data, as long as you have the logic diagram. Okay, if you know which input is active high, which output is active high or active low, then you can figure out the truth table just by yourself. Next, let's talk about the expansion of decoders. Expansion means we can use smaller decoders to build bigger decoders. For example, we can realize a 328 decoder using 224 decoders. If you can recall, for the 328 decoder, the truth table would look like this. Here we just use a simple case, assume everything is active high, both input and output. Okay. Now, but how do we realize this using 224 decoders? Actually, if you observe the truth table needle, if you only look at the first 4 lines here, and let's cut the column here. So let me redraw this. Just look at this part. Does this look like a decoder to you? Right? This looks like the truth table for the decoder, at least for the output part. for the input part, you can see X value is not changed. So basically, I can treat this as a 2 to 4 decoder with active no enable, right? Remember? If I have something like that, the truth table of this would look like that. If I set this as Y, this as Z, this as X, and this as D3, D2, D1, D0. Then we check the, let me change the color. Let's check the other 4 rows and the other 4 columns. This also looks like a 2 to 4 decoder, but with an active high enable. So we have another one. So we can use the same 2 to 4 decoder here. Okay, this is still Y, Z, and what we want is actually X bar here, right? Because this decoder we use is active no with active no enable. So we take the opposite of X, then we can change it to the active high, right? When X equal to 1, X bar equal to 0. So this enable is active, right? So we collect this to D7, D6, D5, D4. And these Y and Y should be collected together. X, Z, and Z should be collected together. Then how do we collect X? Simply we just add a NOT gate here. Then we realize the 3 to 8 decoder using 2 to 4 decoders. Here I show you a second way to do the expansion. Let's check this out. Let's try to use 2 to 4 decoders only to realize the function of a 4 to 16 decoder. So 4 to 16 decoder, we have 4 input and 16 output. So here our first clue is that the output so we have 16 and 4 here. So it's very natural. We think at the output stage we would have 2 to 4 decoder here. Then we can have 16 outputs, right? So the real problem now is how do we select those four decoders at the output stage, so I can get the active output based on the 4 inputs here. Okay. So what we do here is that we can use another decoder, the 5th decoder or D0 here, and use its output to control the enable input of those 4. By doing so, we are basically selecting the right decoder to put the output to be active, right? So how do we select that? That depending on these 2 input, right? So if I call this I3, this I2, so I3, I2, the value of them will determine which decoder here is enabled. Okay, and I can enable this whenever I need it. Okay, right now I just put a logic 1 here, then this is the active high enable, so I put the logic 1, basically mean this decoder is enabled. Right. So if I3 I2 equal to 0 0, y1 will be active. We're sending 1 to this one, so this will be enabled, and the other 3 will not be enabled. Right. And in the enabled decoder, we can use its data input x0 x1 here to determine which output is selected, right? Then we get the capability to select 1 out of 16 output, right? So first we select the right decoder, then second step we select the right output. So basically we can write the basically we can label the output from let's put a different letter, z 0 1 2 3. This will be 0 4 5 6 7 8 9 10 11 12 13 14 15, and we actually can collect all the x0 together, because it doesn't matter at any time, only one x0 x1 in one decoder, only one decoder will work, so only one x0 and x1 will work. We'll do the selection, and similarly we can collect all the x1 together, and here we assume x0 is hybrid, but maybe that's not the usual regular way to do this, so let's change it. So let's say this is I3, this is I2, then x1 will corresponding to our I1 and x0 corresponding to our I0. So then we can try this out. For example, 0 0 0 0, so 0 0 0 here, it will select the first, it will select D1, and the 0 0 here will select the y0 of D1, right, which is, so you select D1 and the output, so Z0 equal to 1, and the 0 0 we still select this chip D1, but this time y1 of D1 will be active, so Z1 will be 1. Okay, next one, 0 0 1 0, still D1, and now y2 of D1 is active, so Z2 equal to 1. And this is also, so Z3 is 1. Now 0 1, 0 1 means y1 is active here, so the D2 will be selected this time, and the Z4 is 1, D2, Z5 is 1, D2, Z6 is 1, D2, Z7 is 1, and 1 0 1 0 will select y2 here, which will select D3. Then Z8 is 1 for 0 0, Z9, which is y1 of D3, and Z10, which is y2 of D3, Z11, which is y3 of D3. Then finally, if I3 I2 is 1 1, D4 is selected, Z12 is 1, D4, Z13 is 1, D4, Z14 is 1, D4, Z15 is 1. So this basically tells you the truth table of the 4 to 16 decoder, right? So we need a 5 2 to 4 decoder to realize one 4 to 16 decoder.